Welcome to the 1977 Nobel Prize in Physics. This one was a joint award between Philip Anderson, Sir Nevill Mott, and John Van Vleck. It went to three individuals. This was for their fundamental theoretical investigations of the electron structure of magnetic and disordered systems, which is a big fancy physics way of saying some stuff, but we'll get to that in a second. Now, they all came at this from a much different angle, and they actually came at it in different decades. So they each added like a layer on top of one another to get you to a lot of interesting applications. So I'm going to do my best because this is really deep in theory to kind of take all the math out. There's not going to be any math, and just kind of talk about how they approached the problem, what the advancement they made was, and more importantly, what applications came out of it that you actually use every single day, thanks to these three gentlemen. Because without the math behind it, the engineers and the scientists can't go build better and better versions of it for you to kind of enjoy. And believe me, with this one, you absolutely do use them. So let's dive in. Now, Philip Anderson was kind of a curious little guy. He always tended to really dig into things from a little bit different perspective than most people. And I'm actually familiar with a great deal of his work, but we're going to focus in on his stuff that led to the Nobel Prize. Now, solid materials like a brick of iron or something, the top of your desk, often have a very ordered structure to them. So the atoms inside there are very ordered, they're very regular, they're very predictable. But sometimes some materials can have a very disordered structure. And some materials like glass actually don't have much of a regular structure at all, depending on the glass. But you can get into these disordered structures very quickly. And those disordered structures have just as much application as the ordered ones. They're just tougher to figure out. So in 1958, Philip Anderson showed how an electron, under the right conditions, can move about freely inside a disordered system, but can also become more or less bound in a particular spot. So it can kind of circle around and around and around in one spot. And what he did to get there was he combined the many body problem in physics and solid state physics. And it really led to this whole new field called condensed matter physics. And he showed through his work that this work he did on electron localization, that electrons can actually become stuck in metals with some impurities. So they kind of get in a spot and they kind of get stuck there. What does that sound like to you? Does that sound like it might have some meaning? Well, this work really led to computer memory devices because electrons getting stuck in a particular spot means the metal can kind of remember it, or the electronics in your computer can kind of remember something. So all of his work on fancy disordered systems and how to get electrons jammed up in one spot inside a material led to the memory you use in your computer, your phone, your television, all over the place. All that is the theory work that surrounds those devices. Now, let's dig into the other two gentlemen because they approach things a little bit differently and actually led to different applications, which I think is kind of cool. Now, all three of these men worked in an area of ordered versus disordered systems. So that's sort of the common theme that we have here. But like I said at the beginning, they came at it from different directions. So now when it comes to electronic devices, the electric and magnetic properties of different materials really, really matter, right? We have to really understand that stuff. And these properties are largely determined by how electrons move around inside there, not just in relation to the nuclei, but also in relation to each other. So like they can flip from one atom to another. Can they move cleanly through something like they do in a copper extension cord or something like that? But we have to really understand how those properties work. So by observing the interaction between electrons in around 1949, Sir Nevill Mott explained how certain crystals that can alternate between electrical conductors and insulators. They can kind of become both in certain ways. And these types of materials have come to be known as semiconductors. So his theory finds direct application in things we find all over the place in our semiconductor materials today. In fact, some of the semiconductors you can see are getting really small, they're getting really interesting, and they're certainly finding application all over our lives. I mean, I look around the room I'm in and I don't see too much besides my desktop that doesn't have a piece of semiconductor material in it. But it's become pretty darn prevalent, which is kind of cool that here's the theory work for it way back in 1949, won the Nobel Prize. So let's dig into part 3 of this particular story. Now, John Van Vleck. Now, to understand his work, I had to go all the way back to the 1930s, and that's when he first developed his theories about how electric fields and crystals can affect foreign atoms, and that foreign atom can be bound to that nearby atoms through those electrons. So he kind of looked at early on, how do you get these materials to kind of work together to do things? So how do you have a new electron come in and kind of get bound to something? And he showed through this work, through how the interactions between electrons and movements can create local magnetic moments inside crystals. And what that led to was things like the transistor, and that led to things like lasers. So his application found working with lasers and transistors. And transistors also, if you remember, won the Nobel Prize in 1956 for the guy who developed the first one. But if it weren't for the theory way back in the 30s, that wouldn't have actually happened. And those transistors, as you can see in the image, are getting pretty darn small, and you can actually now get them with single electron sensitivity, which is pretty darn cool. I mean, the lower the number of electrons you need for a transistor to function, the lower power you can have in your computer, the smaller you can make your laptop with more power in it. Computing power, not electrical power. And also the less electrical power you need to power that amount of computing power. So it's pretty nifty stuff. That also was another interesting thing about John Van Vleck's work was one of his PhD students was his fellow Nobel Prize recipient from this year, Philip Anderson. So one of his students actually shared the prize with him for work the student did 20 years later. But there's cool stuff in this one. And without these three guys, we wouldn't have had the theory that leads to all the devices we use every single day. And occasionally we have to remember when it comes to scientific work, the theoretical side of it, you never know where the application is going to go. It could be something great like electronics. It could be absolutely not applicable to people's daily lives, but you don't know until you get the theory really sorted out. So sometimes you have to kind of go into this with a I don't know where it's going, but let's try it sort of a mentality. But in this case, it went very, very well. So we'll see you on the next Nobel Prize. By the way, the next one is cosmic microwave background radiation, along with some other stuff, which is pretty cool. So we'll see you on the next one. Don't forget to click like and subscribe. And if you want updates when the things come out, you click the bell icon, and it'll send you an alert when I drop a new video. All my videos these days are science or Nobel Prize related. So enjoy. We'll talk to you soon.